All right, let's get started. Obviously, I'll be subbing for you guys today. I record all my lectures. I upload them to my YouTube channel. This will not be an exception. So if you need to reference this lecture, then you have a place to go reference it. Second, you're all sophomores, right? Yes. All right. We're going to briefly have a conversation for those of you that are sophomores. I'm guessing that's the majority, right? And that conversation is about cheating. Now, I know that 75% of you, roughly, cheated your way through Masada, especially when it came to math. You would do stupid things like you'd see the problem, you go plug it into Mathway, and it prints out all the steps for you in the answer, and you just go write it down, and there you go, you can show your work. Now, eventually, you're going to take a math class from me, not this one, but next. And you can't cheat in my classes, because I'm a lot smarter than you, and I'm a lot smarter than that computer that you use. So, for example, give me a simple problem that Mathway can't solve. Something like 2x equals 1,000 factorial. This is real easy for a human to solve. The answer is just x equals 500 times 999 factorial. Go ahead and try it on Mathway and it's going to crash on you, because those numbers are too big for a computer to store. And so I know little tricks like that to make so that you can't cheat in my classes. Plus the types of questions I ask, you're not going to be able to cheat on. You'll get a taste of that at the end of class. So you've got a new class that you're starting here, fresh start. Don't cheat, dedicate yourself to this course, and you'll be fine by the time you get to me. Once you get to me, that won't work. Students never believe me, and I usually have half my students fail. So let's not have a 50% failure next year. Sound good? All right. That's a brief side note, because for some reason, other people don't like to address it. Okay, so starting today's material, I don't really like you guys' book. It seems to just pretty much focus on giving you a bunch of example problems to show concepts. So I'm just going to follow exactly how your book does it. Nothing special. All right. So we'll start with this first example problem. The first example problem, we've got this picture here. This picture is supposed to represent a mobile, like what you put in a baby's crib. That spins around, right? And it's perfectly balanced. Now, what's given to you is that, so you have these rods over here and then a string attached to the rod to some animal, some shape for the child. What's given to you is that each inch of this rod weighs 1 ounce. So this piece of the rod weighs 4 ounces. That's some quick math. All right. And notice that it's also perfectly balanced. When you have a mobile, it's perfectly balanced. It's not tipping one way or the other, right? And as you know from a teeter-totter, if this is perfectly balanced, then the weight here is what compared to the weight here? The same. The same. Perfect. So those are the key things that you look into when you're figuring out how to solve this problem. So the problem tells you each inch of the rod weighs 1 ounce, and it tells you the total weight of the entire configuration is 40 ounces. Our job is to figure out how much this shape weighs, how much these two weigh, and how much this weighs. You understand the problem? Yeah. Okay. So first thing we know is the total weight of the entire contraption is 40 ounces. So what is the total weight? I have the weight of x, I'm not sure what that is, plus I have 2 weights of y, whatever that is, plus I have the weight of z, whatever that is, plus how much rod length do I have there?
8 inches. 8 ounces.
Total.
Oh.
We have 8 inches here, we have 4 inches here. Notice that this is another configuration that's balanced.
14 inches.
14 inches. You see that? In case you can't read my writing, that says 1 inch, 1 inch. 2, 2, 4, 4. 4 plus 4 plus 2 plus 2 plus 1 plus 1 is 14. So we have plus 14, and the total weight of the whole thing is 40. So the sum of all these weights better equal 40. That's one of our equations. Now, I told you that the weight here has to equal the weight here. Right? Or in other words, if we look at just half this contraption, it has to have exactly half the weight. So when we look at all the weights over here, what are all the weights on this side? X and
4.
X and 4. So X and 4 equals what? 20. Perfect. And then finally, everything on this side also has half the weight. Right? Yeah. Well, we don't really need to think about it that way. There's not one right way to solve this problem. Typically, when you have an equation with 3 variables, and if you need to figure out what those 3 variables are, we have x, y, z, you need to come up with 3 equations. So we got one equation right here, we got another equation right here, we need one more equation. Now we could note the fact that all these summed up together is also half the weight. I'm going to do something different. the weight here and the weight here have to be equal. Right?
Yeah.
So what is the weight here?
2 plus Z.
We can even ignore the 2. The actual weight pulling down is just Z. And Z has to be equal to the actual weight pulling down right here.
2y plus 2y.
2y plus 2. Perfect. So there we go. We have 3 equations, 3 unknowns. We should be able to solve for all our variables now. So obviously we know what x is right out the door.
16.
X is 16. So the big one weighs 16 ounces. Sanity check. What I get for Z better be less than what I got for x. And what I get for y better be less than what I got for z. Alright, so that one weighs 16. That sounds about right. Now we know that z is equal to 2y and x is equal to 16. So I'm going to plug those 2 facts into this top equation. So rewriting this top equation, I know that 16 plus 2y plus, I'm going to spell z weird here. Make sure you follow it. Everyone understand that?
Yeah.
I know that z is equal to 2y plus 2. So I have x plus 2y plus z plus 14 is equal to 40. Right?
Yeah.
Now we can just solve for the y. Not particularly hard. Let's get rid of the 16 and the 14 on both sides. So I'm going to subtract 16 from both sides, and I'm going to subtract 14 from both sides. Or in other words, I'm going to subtract what from both sides?
30.
30. So when we get rid of this and this, we're going to be left with 30 over here. Or left with 10 over here, right? So just rewrite that out to make sure everyone's following. So we know that 2y plus this inner term, 2y plus 2, is equal to 10. Right?
Yeah.
Now we're just going to subtract 2 from both sides and combine like terms. If I have 2y and 2y, how many y do I have?
4y.
4y, perfect, is equal to
8.
8. We subtract 2 from both sides.
Yeah.
Right.
Minus 2.
If 2y plus 2 is equal to 10, then 4y better not be 12.
Yeah.
Sanity check. All right, and finally y is equal to 2. And now that we know the weight of y, what's the weight of z?
4.
Try again.
18.
Try again. We know the weight of x. We know the weight of 1y. Now what's the weight of z? 6. Because we know that z is equal to double the weight of y plus 2. Because the weight of z has to cancel out the weight of those 2 y's plus the weight of the rod right there. You follow that?
Yeah.
Okay. That's far and away the hardest problem that they give you in this first section. I don't know why it's the first one, but it's the way that it is. So now we'll move on to the next one. And these ones are so trivial, I'm not sure how much work I need to write for you. If x plus 4 is equal to minus 12, what's x equal to?
Negative 16.
Negative 16. What number do I have to add 4 to get negative 12? Negative 16. I don't know. Find a bunch of different ways to say it. If Frank hands me $4 and I say, Kay, you still owe me 12, how much money did Frank owe me? $16. All right. Okay, B, 12b is equal to 18. What's b equal to?
We don't know that
You don't know that yet. 12b is equal to 18. All right. You know that what you do to one side of the equation, you can do to the other side. There's 2 ways that we do that. You can either add the same thing to both sides. Subtraction is just a different form of adding. Same thing as adding a negative number. Or you can multiply the same thing to both sides. Dividing is just multiplying by a fraction. So if 12b is equal to 18, then 1/12 of 12b better still equal 1/12 of 18.
Okay.
Right?
Yeah.
What's 1/12 times 12?
0.
141.
Holy,
One.
holy.
It's 1/12 times.
If you take 1/12 of 12, how much did you take?
1.
1. If there's 12 slices of pizza, and you take 1/12 of the pizza, how many slices did you take? 1. Not 0, not 144. If you take a fraction of something, you have a smaller portion. Right? Not bigger, not 0, you got something. Just less. All right, so 1/12 times 12 is 1 times b is equal to, now 18 over 12. Wonderful. Now I'm worried you don't know how to reduce fractions.
It's 1.5. Yeah, it's 1.5.
It's 1.5, but what's the fraction way of saying it?
1.5.
3 over 2.
Ooh,
3 over 2.
never an improper fraction. Does Masada allow you to do that? Improper fractions garbage. I don't know what Joanne wants. She shouldn't want you to write something like 5 1/2. That is terrible. That means 5 times a half. Yeah, that notation is terrible. All right. 18 over 12 is the same thing as, what is 18? If we factor it.
3.
And
6.
6 and 3. 18 is the same thing as 6 times 3. Right? Crazy math there? No, nothing crazy about it. 12 is the same thing as 6 times 2. So you have a 6 in the bottom, a 6 in the top. We can rewrite this if we want as 6 over 6 times 3 over 2. What is 6 over 6? 1. What's 1 times 3 over 2?
3 over 2.
3 over 2. Not 1.5, not 1.5, 3 over 2. Oops. Leaving it as unmessed with fractions is ideal. Makes it very clear how you came to your answer. Okay, so there we go. We figured out what B is. Right? 3 halves. Okay, let's try another one. One that's a bit more convoluted. So we have negative 27 plus 6y is equal to 3 times y minus 3. Uh-oh. We've got, hopefully you understand it's implied that there's a multiplies there.
Yeah.
Right?
Yeah.
And hopefully you're all okay with a dot for multiplies rather than this atrocious symbol.
Yes.
Okay. Yeah, never use that atrocious symbol. That atrocious symbol marks a variable. We call it x. We use dots for times. Okay. So, I've got this 3 outside the parentheses. What do I do with that 3?
Multiply by the side.
I distribute it through. We use the distribution property. So I'm going to multiply y by 3, and I'm going to multiply minus 3 by 3, and I'm going to add those terms together. All right. So we'll leave this side the same for now. Negative 27 plus 6y is equal to, we have 3y plus 3 times minus 3. Right? Took each thing in there, multiplied it by 3, added them together. That's the distribution rule. Good? Now the problem becomes relatively trivial. Maybe we'll simplify one more time. Negative 27 plus 6y is equal to 3y what?
Negative minus 9.
Minus 9 or plus negative 9, however you want to say it, it's fine. Minus 9, right? All right, now to both sides, what am I going to do? I'm going to subtract 3y from both sides. You good?
Yeah.
When you get to the point where you just have one equation with one variable, what do? You shove all your variables to one side and all your numbers to the other side, and your answer comes out. So I'm going to shove all my y's over here. So to get rid of the y's over here, I need to subtract 3 y's from both sides. So when I subtract 3 y's from both sides, I have negative 27. How many y's do I have left on this side? 3 is equal to just minus 9. Perfect. All right. Now what do I need to do? I need to get all my numbers to the other side.
Add 27.
Add 27 to both sides. Perfect. And so we get 3y is equal to?
21.
18.
Or is it 18?
18.
If you have a 7 there and you get rid of 9,
Yeah.
you're no longer still in the 20s. Sanity check. 18. So that's 18. Finally, what does y equal?
6.
That was quick. Y equals 6, and we're done. Now, there's always one more thing we can do if it's possible that we made a mistake somewhere along the way.
Substitute 6 in for y.
Yeah, plug 6 back in for y. This better be true when y equals 6. That's the whole thing we were looking for. We were saying what value of y makes this thing true. And it just so happens that this being true is identical to this being true, is identical to this being true, is identical to this being true, is identical to this being true. So if you didn't make a mistake, we better be able to go back and plug in 6 for y to our initial expression here and get the same thing. So let's write that out. So we got negative 27. 6 times 6 is?
36.
36. Let's see. Our initial expression is right here. Is equal to 3 times y. Thank you. That was a trap. All right. Anytime I make a mistake, I just test it here. Okay. Negative 27 plus 36, or 36 minus 27, however it's easier to think about.
9.
9, right? Good job. All right. 6 minus 3 is?
3.
Times 3 is?
9.
Is 9 equal to 9?
Yes.
Okay, thank goodness. We did it right. Okay, nice and simple. Next one. Looks about the same. So our next problem here, don't let me accidentally skip any of these. 3 times 2x minus 1 minus 2 times 3x plus 4 is equal to 11x, right? Okay, first thing I gotta do is distribute the 3 through. So tell me, what am I writing?
6x, subtract 3.
6x minus 3, we'll write it this way for right now, plus 3 times minus 1. Just to make it very clear the rule that we're using. We did 3 times that thing plus 3 times that thing. That's how you distribute. Now this one here, I'm just going to write a plus. We're going to think about this as a minus 2 multiplied for those things. Alright? What's minus 2 times 3x?
Negative 6x.
Minus 6x, so we'll put that in parentheses. Plus minus 2 times 4. Right? So we did that times that plus that times that. Notice that we ignored the plus here, or we ignored the minus sign here. We always just wrote that as a plus. Now it turns out it's going to be a minus when we simplify, but just to make sure you understand the procedure there. Equals 11x. Okay. Finally, let's simplify. So we have 6x. What's this going to be?
Negative 3.
Minus 3. This is going to be minus 6x. This is going to be
Negative 8.
minus 8 is equal to 11x. Everyone follow that? Nothing weird? Perfect. Okay, shoot. Now what?
X is 0 on that side. Shove all the one side.
Wonderful. Collect like terms. So you might have been tempted. Okay, I need a plus 6x to both sides, or I need minus 6x from both sides and plus 6x to both sides. No, combine like terms first before you start manipulating both sides. So here we have an x term and an x term. Let's combine those. If I have 6x and we lose 6x, how many x do I have?
0.
So we have 0x. If we have minus 3 and minus 8, we have minus 11 is equal to 11x. 0x is obviously the same thing as 0. So minus 11 is equal to 11x. Or, what do I do now? Multiply both sides by 1/11. Or divide by 11. But I'm always going to say is multiply both sides by 1/11. Right? So we're going to take that, we're going to multiply by 1/11. We're going to take that, we're going to multiply by 1/11. 1/11 times negative 11 is? Negative 121. No! Negative 1. All right. Just because the teacher says it doesn't make it right. All right. And 11x times 1/11 is going to be?
1x.
Just x. Perfect. Everyone seen that one? Yeah? All right. Nice and simple. Okay, next one. We just did this one, right? Okay, so this one's requires you to think a little bit more, I guess. So we got this shape here, some big rectangle. And all you know is that the width of the rectangle is 3 times the height of the rectangle. You with me so far?
Yeah.
So if the height were 50 meters, what would the width be?
150.
150 meters. Quick math. Wonderful. All right. So now here's the other thing that we're given. We'll redraw the figure over here so we can talk about it. So if this is x, we know that this is 3x. All we know is that this side is 3 times longer than this side. Okay. Second piece of information we're going to give you is that the perimeter of this whole thing is equal to 200 meters. Everyone know what perimeter is?
Yeah.
Okay, so now I need to express that relationship in terms of an equation. So ignoring the perimeter here for a second, how would you tell someone what the perimeter of this thing is? How far is it to go from here to here? 3x. How far is it to go from here to here?
X.
And from here to here?
3x.
And from here to here?
X.
Does that get us all the way around?
Yes.
That's our perimeter. So, if we're going to be a little bit tedious here, it's 3x plus x plus 3x plus x. And that is going to be equal to our perimeter of 200 meters. Now, combine like terms, how many x's do we have?
8.
Did I hear a 6? You guys are going to make me throw chalk at you. All right. So 8 is equal to 200. 8x is equal to 200 meters. Now what do we do?
Divide by 8.
Divide by 8 or multiply both sides by 1/8. 200. Oh, dangerous. Do we know how to divide that by 8?
Yes.
Look, simple tricks. 2 here is the same, or 8 here is the same thing as 2 times 2 times 2. That's the same thing as just divide this in half 3 times.
Oh, okay.
You see that? 200 over 8 is the same thing as 200 over 2 times 2 times 2.
Oh, yes.
Times 1 more 2.
So oh, yes.
What's 2 times 2
4.
times 2?
8.
Wonderful. So we just need to cut this in half 3 times. So if we divide it by the first 2, that leaves us 100 over 2 times 2. Divide it in half again, that leaves us 50 over 2, which is equal to 25. Perfect. So x here is equal to what? 25. Finish your answer.
Meters.
Meters. If I say go that way 25, you're stuck. How tall is he? 52. 52 what? Meters, inches, centimeters? Who knows? You got to give your units, otherwise the number makes no sense in this universe without a unit. So if you're ever talking about the physical universe you occupy, you always need a unit. Otherwise your number is completely meaningless. Come work for me, I'll give you 627. If you're lucky. Alright. Okay, now they want us to do that same problem again, but this time they want us to change the perimeter to being 320. Okay. Now we can erase and resolve, or we could just plug in 320 right here, which is going to be 320 right here. We can erase that. So what if the entire perimeter of this object were 320 meters? Then we know that, same process, right? Okay, 320. All right, now do this in your heads, rather than being lazy. 320 divided by 8.
40.
40?
Yes, it's
Oh, yeah, it's 40.
40 meters.
Positive.
40 meters.
40 meters.
Alright. X is equal to 40 meters. Quick sanity check. If x is 40, what's 40 times 8? Alright. Okay, good. Alright, we did that problem. Now we're supposed to say when the equation is true and when the equation is false. Now, not all equations are true just because I give it to you. Let me give you a simple example. If I say x plus 1 is equal to x plus 2, that's a false equation. That can never be satisfied. Subtract x from both sides and what do we get? 1 equals 2. Is 1 equals 2 true?
No.
How do you know?
Because 1 doesn't equal 2.
What is 2?
1 plus 1 is 1.
That is its definition. We'll get to it. Alright. So, that's what it means for an equation to have no solutions. You get a bunch of nonsense like that. So, when is the equation true? Let's find out. Start with the first one. We have 11 plus 3x minus 7 is equal to 6x plus 5 minus 3. Alright, what's the first thing we should do?
Combine like terms.
Combine like terms. Wonderful. 11 and minus 7 is 4 plus 3x is equal to 5 and minus 3 is
2.
So we have 6x minus 2. No, plus 2. All right. Someone's correcting. Now what should I do?
I will push numbers to one side and variables to one side.
Do I want my variables on the right or the left?
Right?
The right probably seems easier since there's more already over there. All right. So I'm going to subtract 3x from both sides, right?
Yes.
So we're going to get 4 is equal to how many x do I have left?
3.
3 plus 2. Now subtract 2 from both sides.
2 equals
2 equals 3x. So x is equal to
3 over 3. 2 over 3.
1.5.
multiply both sides by 1/3,
2 over 3.
and it's 2 over 3. Right? Or as a decimal,
0.66.
and that's why we hate decimals.
Yes.
And so we just keep in fractions. Okay, so x equals 2/3. And then you can always go back and do your sanity check. When x is 2/3, that equation better be satisfied. We'll do it really quick. 11 plus 3 times 2/3 is equal to
6 over
2.
3.
2. 6 over 3, which is 2. Wonderful. So that's 2 minus 7 is equal to 6 times 2/3 is
4.
4. Everyone see how they're doing this math so fast?
Yeah.
All right. So that's equal to 4 plus 5 minus 3. And let's check. What's 11 plus 2?
13.
Minus 7.
6.
So this all came out 6. What's 4 plus 5?
9.
Minus 3.
6.
6 equals 6. Okay, satisfied. So this equation right here that we started with, there's one and only one number x that satisfies this equation. That's x equal to 2/3. That's the only one that satisfies it. Notice the equation I gave you before, no x satisfies it. There is no x that you can plug into this to make it true. No x satisfied that. One and only one x satisfied this. Good?
Yeah.
All right. Let's move on to our next example. So our next one is 6x plus 5 plus 5 minus 2x is equal to 4 plus 4x plus 1. First thing we're going to do, that is not a minus there, I just didn't erase well. Okay. Combine like terms. How many x's do we have over here?
4.
4. How many constants?
5.
Just 5 is equal to, how many x's we have over here?
4.
5.
Yeah.
All right, now what?
Now we put all the
Variables
variables on
on
one
one
side
side.
and then the 5 or the numbers on the other.
All right, so I'm going to subtract 4x from both sides, right?
Yeah.
When I subtract 4x from both sides, what do I get? Oh, on this side
0. So 5.
is equal to 0x plus 5, right?
Yeah.
Or simplifying, we got 5 equals 5. Now maybe this is far enough that you can already see it, and we don't need to bother simplifying anymore. When is 5 equal to 5?
Always.
What if x is 100? Does 5 still equal 5?
Yes.
What if x is negative 2? Does 5 still equal 5?
Yes.
So when does 5 equal 5?
Always.
Always. So it doesn't matter what you plug in for x. The equation is always true. So we just really saw the 3 cases. An equation that's never true, an equation that's sometimes true, an equation that's always true. Make sense? All right, that's the big idea with those. We won't bother with the rest since you've seen one of each. We'll just jump up to this. Next one. They give you an equation in terms of one variable and hope that you can solve it in terms of the other variable. So how do you calculate degrees Celsius from degrees Fahrenheit? Have you ever had to do that before? So your degrees in Celsius is equal to 5/9. Your degrees in Fahrenheit minus 32. Right? Our job now is to come up with a different conversion. We want to now figure out Fahrenheit from Celsius. You understand our problem now?
Yeah.
So this was given to you. Now we're trying to come up with a way to calculate Fahrenheit from Celsius. This gets you Celsius from Fahrenheit. We want Fahrenheit from Celsius. Good?
Yeah.
Okay. So how do we do that? We need to get f by itself over here. When f is by itself over here, we're going to have f equals something. Something in terms of c. And so that's going to be our conversion formula. So let's go ahead and solve the same way you would, trying to get f by itself. First thing I'm going to do is multiply the 5/9 through. Right? So 5/9 times f plus 5/9 times minus 32. Actually, that's not the way I want to do it. Sorry. That's going to make a mess of things. There's an easier way to do this. I don't want this 5/9 here. It's making a mess for me. I wish it was on the other side. That'd be a lot easier. So you multiply by the reciprocal or divide. So you can divide by 5/9, but typically you ask a student to divide fractions and now they're dead in the water. That's why I usually think about these in terms of multiply. You always just multiply by the reciprocal. So I have a 5/9 here. I want to turn this number into a 1, right? Let me give myself some space here. C is equal to. So if I multiply by 9/5 here, and I multiply by 9/5 here, that's perfectly legal, right? Multiply both sides by the same value. And now what is 9/5 times 5/9?
1.
1. The 5's cancel out with the 5's leaving 1. The 9's cancel out with the 9's leaving 1. All right, perfect. So now, just changing the order on those, 9/5 C is equal to F minus 32. Now what?
You add 32 to the other side.
Add 32 to both sides. So now I get 9/5 C plus 32 is equal to F. Or the way you'll typically see it, F is equal to 9/5 C plus 32. Right?
Yeah.
Let's use it really quick. What's boiling point in terms of Celsius?
100.
100 degrees Celsius. So what is it in Fahrenheit? How hot do you have to get water in terms of Fahrenheit to get to boil? Let's figure it out. So I'm looking for the Fahrenheit, I know the Celsius. So I know that the answer I'm looking for in Fahrenheit is equal to 9/5. In terms of Celsius, we know that it's 100 degrees Celsius plus 32.
So you just.
What's 100 divided by 5?
20.
Times 9, 180. So we got 180 plus 32 is what F is. So what does F equal? 212. There
So
you go.
you just substitute the number for C.
It just converts it. It's saying 100 degrees Celsius is the exact same as 212 degrees Fahrenheit. If you have boiling water and you had a Fahrenheit thermometer and a Celsius thermometer and you stuck them both in there, one's going to read 100 degrees, your Celsius one, one's going to read 212. Similarly, what's freezing point in Celsius?
0.
0.
And what's freezing point in Fahrenheit?
32.
Minus 32, right?
Negative 32.
So notice, let's see, where do we actually have our equation? Our equation's right here. Or positive 32. Why do I think negative? Okay. So, Celsius at freezing point is 0 degrees. What's 9/5 times 0?
0.
Plus 32.
32.
So 32 degrees Fahrenheit is the same thing as 0 degrees Celsius, which is the point where our freeze is at. So what's colder outside? Minus 5 degrees Celsius or minus 32 degrees Fahrenheit?
Minus 32 degrees Fahrenheit.
Minus 32 degrees Fahrenheit. We didn't do the math in our head, we're just guessing based off of how the numbers are growing. Alright, cool. So, I guess I also wanted to do Kelvin, which is way simpler. You ever use degrees Kelvin?
No.
You don't know what 0 degrees Kelvin is? It's absolute zero. It's if you had a perfect vacuum of empty space, what would the temperature there be? And it would be 0 degrees Kelvin. That's what we define to be 0 degrees Kelvin. What would it be in Celsius? Okay, yeah. All right, so to get Kelvin from Celsius is this equation. So Kelvin is equal to your degrees Celsius plus 273. So to get Celsius from Kelvin, you can just tell it to me.
You add 3. Oh, wait. What?
Just subtract 273 from both sides,
Oh, so you
right? Maybe you don't want to see it like that. K minus 273 is equal to C, or in other words, C is equal to K minus 273. So if I tell you it's 0 degrees Celsius, what temperature is it in Kelvin?
Negative 273.
No.
273.
Oh, 273.
I tell you it's 0 degrees Celsius.
Yeah.
It's freezing point of water.
Okay. Oh.
All right. What temperature is it in Kelvin?
273.
273. Plug in 0 for Celsius.
Oh,
And that's how you get your Kelvin. It's impossible to have a negative Kelvin temperature.
No.
0 degrees Kelvin is as cold as temperature as theoretically possible. You can't have a negative Kelvin degree.
Okay.
No such thing. All right, so now what is 0 degree Kelvin in terms of Celsius?
Negative 273.
Negative 273 degrees Celsius.
Yeah.
That's the coldest temperature you can possibly get. All right, so that's the first section. On to the next one. The next section, they're focused on inequalities and graphing inequalities and making sure you can understand an inequality. So to graph inequalities, you have to use what we call the real number line. You are all way too familiar with the real number line. You've probably drawn it 1,000 times in your education career. But here it is. You put 0 there, we come to the right, making our tick marks, blah, 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 and we come to the left, making our tick marks, blah, blah, blah. And we call that 1, 2, 3, 4, 5, and it gets super tedious. 1, 2, 3, 4, minus 5 is right there. There we go. Real number line, right? Now our job is to graph the inequalities on the real number line. So if I tell you to graph x is greater than 4, that means I want you to plot all the points on here where the value is greater than 4. Is the value greater than 4 at -5? No. What about a 0?
No.
What about right at 4?
No.
Okay, so we don't include 4, but anything above 4 we do include.
Yes.
And so you fill that in. Have you seen these graphs 100 times?
Yes.
Oh, wonderful. Okay, so then if I would have told you x is greater than or equal to 4, how do I change this picture?
You just fill in the circle.
Just fill in that little circle. Wonderful. If I told you x was less than 4, what does that look like?
You do open circle other way.
And we would have gone this way, right? And then if I told you x was less than or equal to 4,
You fill in
we
the
would have filled that in. Perfect.
circle.
Now, to save myself from having to redraw number lines, I'm always just going to graph it above the number line. So I don't have to erase my number line anymore. Make sense what I'm saying?
Yes.
All right. 12, 3, 4, 5. Because we're going to have to graph on this thing a lot. So it seems. Okay, this was an example of setting up the inequality. We need to be able to go from a basic sentence to representing it as an inequality in mathematics. So if I tell you we're talking about something, we're talking about 5 fewer than a number is at least 12. 5 fewer than a number is at least 12.
So it would be 5x minus 5 x minus 5 with a
It's at least 12.
okay, so it's greater than or equal to 12.
There you go. This is 5 fewer than a number. We're using x to represent our number. What's 5 fewer than x? X minus 5.
Yeah.
And it is at least 12. So it's greater than or equal to 12. Could be 12, could be more. Does that make sense to everyone?
Yeah.
All right, let's try the next one. The quotient of a number and 3 is no more than 15.
So 3 times x.
X plus 3.
Oh wait, is it quotient?
Hold on.
Is quotient?
The quotient. What's a quotient?
I don't really know.
You don't know quotient? Arithmetic.
Multiplication?
No, that's a product. It's a fraction.
Oh. Okay, so x over.
So the quotient of a number, we'll use x as our number, and 3, so the quotient of a number and 3, that's x over 3, is no more than 15. What does that mean?
So it's less
Less
than
than
15. Yeah.
Less than 15. Is that right?
Yes.
Wait,
No, it's less
Can't
than
be.
Less than or equal to. Thank you. No more than 15. It could be 15. It just can't be more than 15.
I was gonna ask.
All right. So that can bring it over. Now some basic properties about inequalities. Maybe you're already familiar with all these, maybe not, I don't know. If A is greater than B and B is greater than C, then A is greater than C. If I'm taller than Tom and Tom's taller than Ben, I'm taller than Ben.
Yeah.
Pretty simple there? All right, next one. If A is greater than B, then A plus C is greater than B plus C.
Yeah. Yeah.
If I have more money than you, and we both get $10, I still have more money than you. Right?
Yeah.
Similarly, if I have more money than you, and we both pay $10, I still have more money than you.
Yeah.
Yes. Make sense? Adding the same thing to both sides doesn't change the equality. Subtracting the same thing from both sides doesn't change the equality. All right. Now let's look at this one. If A is greater than B, and C is a positive number, then A times C is greater than B times C.
Yeah. Yeah.
If I have more money than you, and we both 10 times our money, I still have more money than you.
Yeah.
Similarly, if I have more money than you, and we both take 1/10 of our money, I still have more money than you. Go ahead.
Are you missing any students?
I don't have a clue. I'm subbing.
Do you guys know?
We have no clue.
Now it seems to make her job easier. All right. So this one makes sense?
Yes.
Okay. Now this one, the one that confuses kids. If A is greater than B and C is a negative number, then A times C is now less than B times C.
Yeah. Yeah.
That one makes sense to everyone?
Yeah.
No one's confused?
No.
I may go over it anyways, just
Okay.
because. 20 is less than 50, right? Now if I multiply both sides by negative 10, then we have negative 200 is less than negative 500. Is that true?
Yes.
No, I need to flip the sign. Negative 500 is way smaller than negative 200. Which one's further left on the real number line?
Negative 500.
Negative 500. So when you multiply both sides by a negative number, it flips the inequality.
Yeah.
In fact, let's just do the proof of this really quick for the case where it's negative 1. Let's do a quick proof. Proof. If A is greater than B, comma, then minus A is less than minus B. With me?
Yeah.
Forgot to write my then, but I think you'll get it. 1. Let A and B be real numbers. Say it in a fancy way. A and B are in the set of all real numbers. R is a fancy symbol for all real numbers. Everything you think about as a number is a real number. Anyone here know what complex number is? Perfect. Then everything you think about as a number is just a real number. All right? So that's a fancy symbol for all the numbers, all real numbers. That just means is in. So A, comma B in the real numbers. Let A and B be real numbers.
Okay.
Introduce you to some big boy notation. All right, let A and B be real numbers. And you're going to see me write S dot T dot a ton because we say it so much in math, but it just means such that. Such that A is greater than B, right? 2. Then it's perfectly legal for me to add the same value to both sides of the inequality and not change the inequality, right?
Yeah.
So that's what I'm going to do. I'm going to add the same value to both sides of the inequality. So then A plus minus A has to be greater than B plus minus A. You with me?
Yes.
And you're going to do it one more time now. Make sure you follow this. A plus minus B is greater than B plus minus A plus minus B.
Yeah.
She's adding more.
So first I added minus A to both sides, then I added minus B to both sides.
Okay.
Follow that?
Yeah.
Now let's simplify. Let's see how much we still have on this side. We have an A, we have a minus A. What do those add up to?
0.
So we're left with just
Negative.
minus B is greater than, and what do we have on this side?
Minus A.
All we have on this side is a minus A. Or, if we prefer to write it the other way, we have minus A is less than minus B. And we're done. That's our proof. Box there means, and thus it is demonstrated. Alright, quick little proof. There you go. We don't need that anymore. Okay. So we went over that. Okay, let's do one of these. So we're supposed to solve and graph. So we're supposed to solve means find all the x's that make it true. And then graph means plot all the points that could be those x's. Alright, so let's do it. We've got minus 3 times 2x minus 5 plus 1 is greater than or equal to 4. Right? First thing we're going to do, let's just try and simplify this side. So I'm going to distribute the minus 3 through. So distributing the minus 3 through this, we're going to get minus 3 times 2x plus minus 3 times minus 5 plus 1 is greater than or equal to 4. I just multiplied the minus 3 through to both those terms and added them together. Nice and simple, right?
Yeah.
Now simplifying, minus 3 times 2x is
Minus 6x.
minus 6x plus or minus
15. What? Just 15.
plus 15, right? A negative times a negative is
Positive.
Right, because if you have negative 3 groups of negative 5 people, you have 15 people. No, it's a little bit weird. You're right, but don't just memorize that you're right. Think about that for a second. How does it make any sense that negative times a negative is a positive? Negative 3 groups of minus 5 people gives you 15 people. All right. But for now, you have it memorized. A negative times a negative is a positive, so you write that, and then we have our plus 1 here. That's a plus, and that's greater than or equal to 4.
Yep.
Wonderful. Now what?
Do you add the
Like terms.
Combine like terms, so we're left with negative 6x plus 16 is greater than or equal to 4. Now what?
Now you put 16 on the other.
You subtract 16 from
Yeah.
We add minus 16 to both sides. Perfect. Add minus 16 to both sides, and we get negative 6x is greater than or equal to
Negative 12.
minus 12, because we added minus 16 to that.
Yep.
Perfect. Now what?
Divide by 6 or multiply by 1.
Divide by negative 6.
Negative 8.
You can multiply by
Multiply
You-
by 1.
Multiply by reciprocal.
Well, you can do it whichever way you guys want. Just getting a lot of answers here.
Divide by
Multiply both sides by, should we do 1/6 or negative 1/6?
Negative 1/6, so you can get rid of the negative.
Let's do 1/6 to start with, just so that we don't get confused in the negative step as well. So we're going to multiply both sides by 1/6. And we're going to get that 1/6 times negative 6 is
Negative.
minus 1. So we have minus x here is greater than or equal to 1/6 of negative 12 is
2.
minus 2.
And then it makes it positive.
Perfect. Now we can multiply both sides by negative 1 or divide both sides by negative 1, however you want to think about it. But if negative x is always greater than or equal to negative 2, then x is always less than or equal to 2.
Oh, fancy.
Oh, yeah.
Okay.
You did the flip. They're not
Yeah, we did the flip. Here, let's try and make the flip appeal with your intuition. Give me a number that works here.
6. Wait.
What?
6.
Negative 6.
1.
Yeah.
6 works here,
Alright.
right? Because negative 6 is greater than or equal to negative 2.
Yeah.
No!
Wait, what?
Negative 6 is.
No.
Negative 6 is less than.
Oh, wait, yeah.
All right. So what's a number that could work here?
1.
1.
1 could work here. Negative 1 is greater than or equal to negative 2.
Yeah.
What's another number that could work here?
0.5.
Negative 1.
Negative 1,000. What's negative 1,000?
1,000.
Oh, that's what you're saying.
Okay.
1,000.
So notice that numbers, you can go, any negative number you want works here, as well as the positive numbers up to 2. Right? Which is exactly what this is. It's all the numbers less than or equal to 2.
Okay. Yep.
You see that?
Yeah.
Clicking with your intuition here rather than just memorizing stuff.
Wait. It can't be, it can't be less than negative 2, right?
Right
It
here?
can't be any negative number.
Try it. So let's rewrite it. We have negative, give me a negative number.
Negative 10.
Negative, we'll do negative 2 like you said. Is it true that that's greater than or equal to negative 2?
Yes.
Yes.
Yeah.
So plugging in negative 2 does work.
Yeah.
Okay. Yeah. But like, what about negative 4?
What's negative? Negative 4.
Positive 4. Wait.
Oh. It still works.
Notice what couldn't I plug in? I couldn't plug in just 4.
Because it'd be negative 4, which would be
Good.
less than
Right.
negative 2.
So, since 4 doesn't work here, 4 better not work here. Can I plug 4 in for this?
No.
No.
No. Can I plug negative 4 into this?
Yes.
Yes.
Can I plug negative 4 into this?
Yes.
Because they're saying the exact same thing. All right. Clicking with our intuition?
Yes.
Yes.
Wonderful. Okay. Oops.
We need graph.
We were supposed to graph it.
Yeah.
What did we end up with? X is greater than or equal to 2?
Yeah.
Yeah.
No, it was less than.
Less than.
Less than 2.
Can't trust you guys. All right. Now, how do we graph out on the number line? You know how to do this. Am I using circle or dot? Dot.
Oh, I mean dot. Oh, that's what you mean.
Oh.
Circle's just a border. If I say look at the circle, we're talking about a boundary. This point is not on the circle.
Less than or equal to.
This point is on the circle.
What's
Circle is just a boundary.
That's nothing.
And then a dot isn't a well-defined mathematical object, but I trust you follow me. All right, now which way do I put my arrow? To the left or the right?
left?
We're going way right.
Oh, I meant that.
No, you didn't. I lied.
I did it.
All right. So that is how we would solve and then graph that solution. You want another one? Yeah, no? You're dying for more math?
Yeah.
I can see it in your eyes. You can hardly contain yourselves. All right. I think we're on this one. So we have -2 times x plus 9 plus 5 is greater than or equal to 3. Right? What should we do first?
Combine like terms.
Distribute. Distribute, distribute, distribute. So distribute the -2 to that and the -2 to that. So -2 times x is -2x plus -2 times 9 is -18 plus 5 is greater than or equal to 3. Right?
Okay.
Now what? That's a minus sign. Now what do we do?
Combine like terms.
Now we combine like terms. -2x minus 13 is greater than or equal to 3. Now what?
Add
13 to both sides.
Add 13 to both sides. Perfect. And we're going to get -2x is greater than or equal to 16. Now what?
Now you divide it
Multiply
by
or divide? Multiply by 2.
Multiply both sides by 1/2. Right? And so now we're going to get -x is greater than or equal to
8.
8. Thank goodness. All right.
So x is greater than or equal to -8.
So x is greater than or equal to -8.
Yeah.
She did. Oh, no, she didn't. Sorry.
Why do I need to? There's not negative on both sides of
Doesn't matter.
Does not.
If you're going to multiply or divide both sides by -1,
I
flip the sign.
Yeah.
Always and forever. So x then is going to be less than or equal to -8. And then always do sanity checks. Does 10 make this true?
No.
No. Does -10 make this true?
Yes.
Does -10 make this true?
Yes. Yes.
Wonderful.
Yes.
So we didn't cheat. So if you're going to get confused by that tricky step of multiplying or dividing by -1, I suggest that you save it as the very last step.
Okay.
Now, some of you, that will become tedious. You can see far enough ahead, but it's a good thing to fall back on. Okay, so that finishes everything on the left, right? Oh, shoot. We still need that real number line. I think we got to graph more of these.
Well, you have to put an 8 on it anyway, so.
Oh, we didn't graph it, did we?
No. Nope. It's just negative. It's x is less than or equal to -8.
All right. So this problem hates me. 5, 6, 7, 8. All right, there's our -8.
It's a dot.
So it's going to be a dot, and it's pointing to the right.
Left.
Oh, okay. There we go. All right, so now, draw my squiggly line that tells me to move my camera. And okay, that should be good. All right, now we're looking over here. All right, this next example, more real-world type example. You're getting a Netflix subscription, and Netflix offers you 2 deals. Deal 1, you can just pay $36 a month. Deal 2, you can pay $15 a month plus $1.50 for every movie you watch.
Deal A.
Maybe. Depends on how many movies you watch. Right? If you're only watching 1 movie a month, you're going to take plan B.
Yeah.
If you're watching 100 movies a month, you're going to take plan A. The question is what's the minimum number of movies that suddenly makes plan A worth more than plan B? Yeah. So initially, if you don't watch any movies, plan B is the better one.
Yeah.
If you only watch 1 movie, plan B is still the better one. If you only watch 2 movies, plan B is still the better one. How many movies can you watch with plan B still being the better one?
You gotta figure that out.
You gotta figure that out. Gotta do a little bit of math here.
Yeah, you are. Just kidding.
So we want to know when 36 is greater than or equal to 15 plus 1.5 times however many movies we watch. what's the biggest n can be? Here we're representing the cost of plan A. Here we're representing the cost of plan B. Or sorry, other way. Plan A is just $36 a month. Plan B is $15 a month plus $1.50 for every movie you watch. Then we're using n as a variable. We could have stuck an x in there if that's throwing you off. Same thing, right?
Yeah.
So we want to know, when is this true? We want to know all the x values that make this true, right? So that's what we're solving. So first step that we're going to do,
Wait,
Substitute something in for x.
combine like terms.
Combine like terms.
no, we're solving for all when this is true for x. Combine like terms. Okay, we got all our numbers together and all our variables together. All right.
16.5.
Now what?
What?
Subtract 15 from both sides. Come on, people.
Sorry.
Right?
Yeah.
All right. So 36. You got to speak up. 36 minus 15, 21, is greater than or equal to 1.5. I'm going to rewrite that as 3/2. Easier to think about that way. X. You with me?
Yes.
Now what am I going to do?
Divide.
Divide or multiply both sides by?
Reciprocal to a reciprocal.
Multiply both sides by the reciprocal of that fraction. Everyone know what the reciprocal means?
Yes.
Just flip the denominator and numerator. So the reciprocal of 3/2 is 2/3. Greater than or equal to, and 2/3. So I multiply both sides by 2/3, right?
Yep.
2/3 times 3/2 is?
1.
Wonderful. 2/3 of 21 is?
14.
14. How do we do that? Divide by the 3 first, then multiply by the 2. Make sense?
Yep.
1/3 of 21 is 7, times 2 is 14. So we get 14 is greater than or equal to x. So as long as the number of movies that you purchase is less than or equal to 14, plan B is fine. If you watch exactly 14 movies a month, then it doesn't matter which plan you use, you're going to pay the same. If you watch more than 14 movies a month, now you better switch to plan A. Pretty simple?
Yep.
All right. So answer the question, when is A a better plan than B?
After 14.
After, if you're watching more than 14 movies. Wonderful. Shouldn't erase these so quick. All right. When is the inequality true? Okay. So remember last time we did when is the equation true. Now we're doing when is the inequality true? Or what values satisfy the inequality? It could be every value, it could be no values, it could be just some values. Alright, so let's go through some of these. Starting with this one, we have -2 times 3x plus 1 is greater than -6 plus 7. Is that right? Hope I wrote that right. It seems weird that they do that. Oh well, we'll assume I wrote the problem right. Okay, what's the first thing I'm going to do?
Distribute.
Distribute. Wonderful. Tell me what to write.
-6x.
Minus 2 is greater than, and we'll just combine these right now.
1.
All right. Okay. Now, what am I going to do?
Add 2 to both sides.
Add 2 to both sides. So we're going to get -6x is greater than.
3.
3.
All right. Now what are we going to do?
Multiply.
Multiply by
1 over 6.
1/6. Perfect. So we'll do 1/6 that. We'll do 1/6 that. And what do we get on this side?
1.
X
One.
equals
Negative x, right?
Yeah.
Negative x is greater than.
2.
1/2.
3 over.
1/2.
1/2. All right. Yes, 3 divided by 6 has to be smaller than 1.
Now flip the
Now
sign
x is
and
less than
negative
-1/2.
Perfect. Now x is less than -1/2. There we go. So that is when the equation is true. When is this inequality true? When x is less than -1/2. All right. And you can always do sanity checks really quick. What's a number less than -1/2?
Minus, or
-1.
-1. -1 is less than -1/2. So let's plug that in here and make sure it satisfies this. So we're saying that -2 times 3 times -1 is -3 plus 1 better be greater than -6 plus 7. That's a 1 parenthesis. Let's make sure that's true. What's -3 plus 1? -2 times -2 is 4. So over here we get 4. What do we get over here? 1. Is 4 greater than 1?
Yes.
And it worked. Alright. Let's do the next one. We got 5 times 2x minus 3 minus 7x is less than or equal to 3x plus 8. Right? First thing we're going to do, distribute. And we're going to get 10x minus 15 minus 7x is less than or equal to 3x plus 8. What's next? Combine like terms. 10 and minus 7 is? 3. So we have 3x minus 15 is less than or equal to 3x plus 8. Now what should we do? We want to get all our x's on one side and our numbers on the other side.
Add 15 to both sides.
Add 15 to both sides? Okay, so then we get 3x is less than or equal to 3x plus... Is anyone going to check her on that?
23.
You sure?
Yes.
I just want to make sure it's not just one student thinking. Alright, 23.
And then you subtract 3x.
Let's subtract 3x from both sides and we get 0 is less than or equal to 23. When is that true?
Sometimes.
If x is 100, is 0 less than or equal to 23?
Never know.
But isn't it less than 23?
Question, is 0 less than or equal to 23?
Yes.
Yes. What about if x is a golden dragon? Is that still true?
Yes.
What about if x is a pink umbrella? Is 0 still less than or equal to 23?
Yes.
So it doesn't matter what x is. This is always true. It couldn't care less what x is. You see?
Yeah.
Alright. 0 less than or equal to 23, that's always true.
Okay.
Okay. So it doesn't matter what x is. And so this inequality will be true here, no matter what you plug in for x. Let's plug in 0 just because it's the easiest. Just to validate really quick, right? So we have 5 times 2 times 0, 0 minus 3 minus 0 is less than or equal to 8, right? And then we get minus 15 is less than or equal to 8. Is that true?
Yes.
Ah, so plugging in 0 for x worked.
Yes.
Okay. So this one was sometimes true, this one was always true. I wonder what the next one's going to be.
Never true.
Only one way to find out. Alright, 2x, call the author, right? Minus 3 is less than 8 times x plus 1. First thing we do? Distribute. Plug that through, we're going to get 8x minus 12 is less than 8x plus 8. Right?
Yep. Yeah. Okay.
Now what?
Combine like terms.
Plus 12.
We combine like terms, we combine like terms. Okay, what?
12. Add 12.
Add 12 to both sides. Okay, so now we get 8x is less than 8x plus 20. Wonderful. Now what?
You subtract 8x from the other side.
Subtract 8x from both sides and we get 0 is less than 20. When is that true?
Always.
Always. Perfect.
Therefore, always never guess. Yeah.
So we had a sometimes, an always, and an always. Okay, now we're on solving graph. Oh, but this is giving us 2 inequalities. Okay, so now we get 2 pieces of information about x. We know that x is a number such that when you double and add 1, it's always more than 7. And x is a number such that whenever you triple it, it's still less than or equal to 18. That's the information we have about x. So let's write these out really quick, and we're just going to solve them the same way that you know and love, and then see what we do with this compound information. No, that's right. So we have 7 is less than 2x, I keep losing it, plus 1, and then we also have 3x is less than or equal to 18. Did I write that right? Yes. Okay. So, working with this one, what do we know? What should we do?
Subtract 1 from both sides.
Subtract 1 from both sides, so we get 6 is less than 2x, or in other words, we get
3
is less than x.
3 is less than x, or if you prefer to write it this way, x is greater than 3. Same thing, right? So x is greater than 3. Where's that on the real number line?
3,
Go to 3, circle, and we're going to the right. All right, now our information from this, if 3x is less than or equal to 18, then what do we know?
Oh, divide or x equals.
Multiply both sides by 1/3, 1/3. What do we get?
X equals less than equal to 6.
Perfect. So then, if we had 6 on our number line here, and if we were to graph this, we would do a solid bubble at 6, and we would go to the left, right?
Yep.
Now, if I tell you that x satisfies this, and x satisfies this, then x has to be from here to here. It has to be one of these numbers. These are the only numbers that satisfy both this and this. These are the numbers that are less than or equal to 6 and greater than 3.
Okay.
Pretty straightforward?
Yes.
All right, let's try another one. Lost my place again. We're right here, right? So we have 5 is less than 3x minus 1, and 2x is less than 12. So we'll start with this one. What should we do? Add 1 to both sides. So 6 is less than 3x. Now what do we do?
Multiply.
Multiply both sides by 1/3. What's 1/3 of 6? 2. What's 1/3 of 3x? X. Perfect. So we have 2 is less than x.
Okay.
So far, what do we know about x? We know it's less than 2, so come to 2. And we're looking at these values, right? Okay, so x has to be one of those values. And x has to satisfy this. So if 2x is less than 12, then what do we know?
X is
Multiply by 1/2, so we get
X is less than 6.
x is less than 6. Where is x less than 6? That's starting right here and going back, right?
Yep.
So where is x less than 6 and x is... Oh, this is greater than 6.
Yeah, I was gonna say, it needs to go the other way.
Oh, yeah.
Wonderful.
So it's 3, 4, 5, and 6. And not 3, 4,
Perfect.
5.
So it can be this value up to, but not including this value,
Yep.
right?
Yep.
So 2, 3, 4, 5, and 6. I don't know, are you guys used to interval notation? 2 to 6, not including them. That's the interval.
In between.
Anything in between 2 and 6. Perfect. All right, so now we're going to try an or one rather than an and. So this time I tell you k is a number such that 7 plus k is greater than or equal to 6, or 8 plus k is less than 3. That's a less than 3. All right, let's take it one at a time. What should we do here? Subtract 7 from both sides. And so we get k is greater than or equal to -1. What should we do here? Subtract 8 from both sides, and we get k is less than -5. Right?
Yeah.
Now when we graph this one, k greater than or equal to 1, where does that go?
-1.
Oh, thank you. -1. Good. So we're going to have a solid dot at -1.
And then right.
And then we're going to the right. So k could be here, or k is a number less than -5. So go to -5, and now we're going to the left this way. So k is in this set, or it's in this set.
Okay.
If you pick any number in here, it'll work. If you pick any number in here, it will work.
But it will never be in between.
But it can't be a number in between. So if we pick a number in between -2, and we plug it into both these, they're both going to be false. Let's check that really quick. 7 minus 2 greater than or equal to 6, is that true?
No.
No. 8 minus 2 less than 3, is that true? No. So is it the case that this is true or this is true? No, they're both false. Now let's try another one. Let's try 1. So if we plug in 1, 7 plus 1 is
8.
8 greater than or equal to 6, is that true?
Yes.
Yes.
Let's look at this one. 8 plus 1 is 9. Less than 3, is that true? No. So is it the case that this is true or this is true?
Yes.
Yes. So with the and, they both have to be true. With the or, just one of them has to be true.
Okay.
Follow that?
Yeah.
Okay. And we won't bother doing the last one. Same type of thing. I think you've got the hang of these. All right. Last section we're covering today has to do with absolute values. Do we all know what the absolute value function is? What's absolute value?
It's how far away the number is from 0 on the number line.
Unfortunately, that's the way you're always told it. Alright, here's the exact definition of the absolute value of x. The absolute value of x is x if x is greater than or equal to 0. It's negative x if x is less than 0. This definition does in fact give you, if you plug in a real number, its distance from 0 on the real number line. That's a wonderful coincidence. Not its definition. Here's its definition. Alright. So following this definition now, what's the absolute value of 3?
3.
3. What's the absolute value of negative 3?
3.
Using the definition, what's the absolute value of negative 3? Negative 3. Which happens to be 3. Isn't that a wonderful coincidence?
Yes.
But it's negative 3, and yes, that simplifies to 3, but you better understand this step here. Otherwise, it's really easy to get confused by the simple definition. Give you an example. If a is a negative number, what's the absolute value of negative a? It's just positive a, right? No, it's negative a. If a is a negative number, then the absolute value of negative a is negative a.
Oh, yeah. Okay.
Let's do an example. Let's say that a is equal to negative 2. A is a negative number. So what's the absolute value of negative 2? It is equal to, it's equal to negative 2. Right? Which equals 2, but it's not the same thing as a. A is negative 2. So if a is a negative number, then the absolute value of negative a is negative a. If a is a negative number, like negative 2, the absolute value of negative 2 is negative 2. You follow that?
Yes.
Kind of?
Yes. Yes, we do.
There are lots of negatives there. Right? And I don't like the way that you get comfortable working with absolute values by just getting rid of negative signs. And you think that that's how you do it, just get rid of the negative. No, that is not how you do it. It just so happens that they always just give you simple problems like absolute value of negative 7, rather than asking you something like absolute value of negative a. We make it a little bit more complex, and now kids are thrown for a huge loop. Because even though you saw the exact definition before, in your brain all you were doing over and over again is just dropping negative signs. No, sometimes a negative sign makes a number positive. Right? So we can't just go around dropping negative signs willy-nilly. You have to actually think about it. So there's our exact definition. Here's the definition of absolute value. Good?
Yeah.
All right. So now let's do some more kiddie problems. Solve and graph each of these. Start with A. So we have the absolute value of 2x minus 1 is equal to 5. Now, it is okay in your intuition to think what values on the number line satisfy this expression. What points up here are such that if I take 2 times that point and minus 1, its distance from 0 will be 5. That's perfectly fine intuition. It's a perfectly fine way to think about it. I just don't want you to forget what the actual definition is and go around dropping negative signs. Alright, so now we're solving this problem. What number is such that if I double it and subtract 1, its distance from 0 on the number line is 5?
6. No.
6? 2 times 6 is 12, minus 1 is 11, and its distance for 5?
No.
Right, so no, that's not right.
Is it?
It's 3 because it's supposed to equal 6.
3 works. 3 happens to work. Is there another number that happens to work?
Negative 3.
Negative 3? What's 2 times negative 3?
-6.
Minus 1. So you were almost at the right idea. Not negative 3, it's going to be negative 2. 2 times negative 2 is negative 4, subtract 1 is negative 5. Absolute value of negative 5 is 5. So those are the numbers. Okay, we figured that out by thinking about it. Now is there a way that we could have just computed that? When is the absolute value of this thing equal to 5? That happens when 2x minus 1 is 5, or when 2x minus 1 is negative 5. Oops. Negative 5. If this whole thing inside the absolute value sign comes out to minus 5, what's its absolute value? 5. If this whole thing comes out to 5, what's its absolute value? 5. So if this whole thing is equal to 5, or this whole thing is equal to negative 5, then taking the absolute value will give you 5. You see that? That's how we think about this. So we need to see where this is true, and we need to see where this is true. So if 2x minus 1 equals 5, what's x? Plus 1 to both sides and divide by 2?
3.
X is equal to 3, right? What's 5 plus 1?
6.
Divided by 2?
3.
There we go. Over here, what are we going to do? Add 1 to both sides, which gives us 2x equals negative 4. Then divide by 2 gives us x equals negative 2. Am I doing that too fast? No. Okay, so those are two numbers. Now if you were told to plot it, how do you plot it? You simply go to wherever 3 is, 1, 2, 3, and you put a dot there, and you go to wherever negative 2 is, and you put a dot there. And so it's just going to be a graph that has just 2 dots on it.
Okay.
That's it, because there's only 2 numbers. Notice that when you had something like this, x is less than or equal to 2, how many numbers satisfy that? Infinite. That's why we have to draw a whole line. So if it's just a couple numbers satisfying it, those are just going to be those points. Okay, cool. Next one. This time we have absolute value 3x plus 2 is equal to 4. Am I reading that right? B right there. 3x plus 2 equals 4. Okay, so when is this true? It's true when 3x plus 2 equals 4, or when 3x plus 2 equals negative 4. Those are the two scenarios that make this true. So it's true when 3x plus 2 is equal to 4, and it's true when 3x plus 2 is equal to minus 4. Wonderful. Now just do the algebra the way you know and love. Subtract 2 from both sides gives me 3x is equal to 2. Multiply through by 1/3 and we get x is equal to 2/3. Follow that?
Yep.
Yeah.
So if we were plotting it, we'd go up here to 2/3. 2/3 is between 0 and 1, somewhere right there, and we put a point there. This one, what do we start by doing?
Subtract 2.
Subtract 2 from both sides, so we get 3x is equal to negative 2, right?
Negative 6.
Negative 6, okay. And then divide through by 3, or multiply through by 1/3, and we get x is equal to negative 2. Good job. And so then you go and you stick a dot, negative 2, if you're graphing it. All right, next one. We'll see one more of these. One that has a number on the, oh, both of them do, good. Okay, so this one has 3 times the absolute value of x plus 2 minus 1 is equal to 8. Well, shoot. When is that one true? We're stuck, right? We wanted the absolute value all by itself, and we don't have that. Let's get it by itself. So we can still just add 1 to both sides. That doesn't change anything. So we can say that 3 times x plus 2 is equal to 9. This and this say the exact same thing, right?
Yeah.
All right, now what can we do?
Divide by 3.
Yeah, multiply both sides by 1/3. And now we get the absolute value of x plus 2 is equal to 3. Okay, now when is that true?
When
The
it's
absolute value of that equals 3 or negative
3 or negative 3.
When x plus 2 is equal to 3, or when x plus 2 is equal to minus 3. Perfect. And then we just solve, right? And so this comes out to x equal to 1. This comes out to x equal to minus 5. And those are 2 values that make that expression true. And once again, you're right, you made a mistake. Not sure you got it right, plug back in. We take our minus 5, we plug it in here. 3 times the absolute value of minus 5 plus 2 minus 1 equals 8. Let's try that. What's negative 5 plus 2?
Negative 7.
What's negative 5 plus 2?
Negative 3.
Negative 3. What's the absolute value of negative 3? What's 3 times 3?
9.
Minus 1?
8.
And it worked. All right. All right. Extraneous solutions. Okay. So notice that in this problem, all of our x's. Oh, I erased the actual problem. It's okay, we have it written somewhere here. Notice that with each of these problems that we solved, all the x's were inside the absolute value sign. Now, when the x's sneak outside the absolute value sign, like with the problem right here, we have to be a little bit more careful. And we'll get sometimes what we call extraneous solutions, and we'll see what that means here. So we're looking at the problem, ignore that. We're looking at the problem, the absolute value of 3x plus 2 is equal to 4x plus 5. All right, when is this true? It's potentially true when this value, we're going to basically do exactly what we did with the previous problem. If I told you that 3x plus 2, the absolute value of that, is equal to negative 5, or is equal to 5, I mean, then when is this true? When the absolute value inside of here is equal to the positive version of this number and the negative version of this number.
Yeah.
Same thing here. When could this potentially be true? When it's equal to the positive version of this number or the negative version of this number.
Okay.
Because 4x plus 5, that's just a number.
Yeah.
All right? So this can be true when 3x plus 2 is equal to 4x plus 5, or when 3x plus 2 is equal to the negative version of this number. What's the negative version of that number?
Negative 4x.
Subtract 5. Plus negative.
Plus negative with the minus plus.
Yeah.
Just multiply this whole side by minus 1.
Yeah. So distribute it. So
Subtract
negative
negative
4x
4,
minus 5.
subtract 5.
Right. Not subtract 5, subtract 5.
Subtract
We're not asking, we're saying. All right, there we go. So these are our two equations, and now you just solve them the way that you know and love. So what should we do? We got to get all our x's on one side, all our numbers on the other side. Right? So what should I do first? Subtract 2 from both sides, so we get 3x is equal to 4x plus 3. All right, now what? Subtract 4x from both sides. So then we get negative x is equal to 3. Now what?
You
Get the negative to the other side.
multiply by negative 1.
Multiply both sides by negative 1, and we get x is equal to negative 3.
Yeah.
Okay.
Sounds good.
Did a little bit of a long way, but that's fine. Lots of ways to do the same problem. Now let's do this other one. What should we do first?
We get all our like terms to the same side.
So what should I do?
Plus 5.
Plus 5 to both sides?
No.
Let's plus 4x to both sides.
Minus 2.
Subtract 2.
All right, we'll subtract 2. Okay, subtract 2 from both sides. And so we get 3x is equal to minus 4x minus 3, right?
7.
Okay. Good.
Add 4x.
Add 4x to both sides. And so we get 7x is equal to minus 7. And in this case, we just got x is equal to minus 1.
Yeah.
Okay. Now, danger, danger, danger. These are our two potential solutions for x.
This is an or. Like,
Kind of. Not with this one. So with this one, your absolute value of a quantity can never be, the absolute value of a quantity can never be negative. Wonderful. There's no notion of negative distance. He's negative 14 feet tall. Makes no sense. Right? So there's no notion of negative distance. So your absolute value can never be negative. So The danger that you run into with problems like these, where you have the variable inside and outside the absolute value, is some of your discovered solutions might make your absolute value come out a negative number, which is impossible. So these are your only potential solutions, x equals -1, x equals -3. Now if I plug in x equals -1 into this, we're going to be fine. If we plug in -1 for x here, what do we get? 3 times -1 is? -3 plus 2 is?
-1.
Absolute value of that is? 1. Over here, 4 times -1 is? Plus 5 is? 1. And it works. 1 equals 1. So that one worked. Now let's try the other one. Let's plug in -3 this time and see what happens. 3 times -3 is? Plus 2 is? Absolute value of that is? Is equal to 4 times -3 is?
12.
Plus 5 is?
-7.
And is the absolute value of 7 equal to -7? No, we can't get negative solutions. You can't have absolute value equals a negative number. So this solution makes this a negative number. So they have the same quantity, but the signs are different. So this is not a solution. So this equation has one and only one solution, x equals -1.
So you have to test.
So you have to test these ones. And hopefully it's pretty obvious to you when you look at it. If I plug in -3 over here, we get a negative number. I know that can't be it.
Isn't the rule that you have to, like, if you're taking away the absolute value, you put the other side negative? Isn't that the rule?
They will tell you that the rule is when you have the absolute value, then it could be the positive version of this or the negative version of this. Potentially both. That's what they'll tell you the rule is, but just reason about it the way we've been reasoning about it. I'd rather you think about it than memorize some rule. I know you guys think that math is just memorizing a bunch of rules, but that is far from the case. The reason people like me love mathematics is because you don't have to memorize anything. Hardly. It's all the other fields that you have to memorize stuff. But you guys are taught formula. If there's a problem it applies to, memorize the formula, and then plug it in and solve. Which is too bad. Okay, what were we on? Were we down here or were we up there? We were up here. Let's do the last one. Absolute value of 5x minus 2 is equal to 7x plus 14, right? So if the absolute value of 5x minus 2 is equal to this number, then that can happen when 5x minus 2 is equal to the positive version of that number, 7x plus 14, or it can happen when it's equal to the negative version of that number. So I can have 5x minus 2 equal to negative 7x plus 14, right? Minus 14. Is anyone still out there? You guys checked out? You still here?
Yes.
Ah, that's good. All right, now what are we going to do? Add 2 to both sides. So we get 5x is equal to 7x plus 16. Now what? Minus 7x from both sides, so we get minus 2x is equal to 16. Now what?
Why isn't it 5x plus 2?
So from here to here, we added 2 to both sides.
Okay. Well, I'm saying the
Did I write the problem?
value, the absolute value should be 5x plus 2, right?
No. That is exactly what I don't want you to start thinking. Let's go back to our simple example. If I told you the absolute value of 5x minus 2 is equal to 3, then that means that 5x minus 2, this inside part here, can either equal 3 or it can equal negative 3.
Okay.
If this inside part here equals negative 3, take the absolute value, you get 3. If this inside part here equals 3, take the absolute value, you get 3. Those are the two cases.
Okay.
So we'd split this into 2 equations. We can have 5x minus 2 equal to 3, or we can have 5x minus 2 equal to minus 3. And now we're doing the same concept, we just happen to have an equation over here rather than one number. That make sense? Perfect.
Just depends on the answer. Like,
You never change the sign of the thing inside the absolute value. So notice that the signs of this are the same here and here, the same here and here. It still doesn't even matter if this was a negative 5x. Then you put negative there, negative there. You don't change the signs of the things inside of here. Make sense? Because this whole thing has to either equal 3 when it's all said and done, or this whole thing has to equal negative 3 when it's said and done.
Okay.
As long as it does that, we're fine. So, this whole thing inside of here has to equal the same thing as, has to be the same quantity as this, but potentially with different signs. I don't know. Bad way to say it. Keep thinking about how we would think about it. Sometimes you explain it again and you confuse people who already understood. So 5x minus 2 has to either equal the positive version of that, or 5x minus 2 has to equal the negative version of that. So here's it equal to the positive, here's it equal to the negative. We were working with the positive. Going from here to here, we add 2 to both sides. Going from here to here, we minus 7x from both sides. Going from here to here, we multiply both sides by minus 1/2. Good?
Yeah.
All right, so x equals minus 8. That's one potential solution. Now looking at this one, what should we do first? Add 2 to both sides. So we get 5x is equal to minus 7x minus 12, right?
And add 7x.
Add 7x to both sides. What's 7 plus 5? 12x is equal to minus 12. So x is equal to? So x is equal to minus 1. So these are our 2 potential solutions. Now, since all our x's were not inside the absolute value, we could have an extraneous solution. One of these could be a bad solution and actually not work.
Okay.
If I plug negative 1 into this, is it going to work? Yes.
Yeah.
Negative 5 minus 2 is negative 7. Absolute value gives us 7 is equal to negative 7 plus 14 is 7. 7 equals 7. Okay, that one works. Negative 8 doesn't work. How is it obvious that negative 8 doesn't work?
Negative 8 times 7 is greater than 14.
Yeah, if you do negative 8 times 7 here, what's that? Negative 56 plus 14, still a negative number.
Yeah.
You can never have absolute value equals negative number. So this one definitely doesn't work.
Is it always the negative 1?
No,
No, I'm
these are
saying,
just
is it
coincidences.
always, okay.
These are just coincidences with the problems we've been given.
Okay.
The way that you have to validate whether, and you may have a problem where both solutions work. Don't think it's always one's right and one's wrong.
Okay.
Maybe they both work. So, you just have to test each of your solutions. Okay. So that answers that. Now solve and graph. So now we're talking about graphing absolute values. And let's get a fresh number line here, since we scribbled all over that one. All right, 0, 5, minus 5, good enough. We can guess from there. All right, so we have the absolute value of x is less than 5. When is the absolute value of x less than 5?
When it's negative 5 or
When it's negative, when it's anything.
when it's negative 5 or 5.
Okay. Let's,
Negative 4 or 4?
yeah, let's think about some numbers. Can I plug 0 into there?
Yes.
Yes.
Can I plug in 2?
Yes.
Can I plug in negative 2?
Yes.
Yes.
Can I plug in 3?
Yes.
Negative 3?
Yes.
4?
Yes.
Negative 4?
Yes.
Negative 6?
No.
6?
No.
Okay, wonderful. So the absolute value being less than 5 is the same, the absolute value of x being less than 5 is the same as take the negative version, stick it here, and add a lesson. Let me just show you and then explain it. Minus 5 less than x less than 5. So when you have an inequality, to get rid of the absolute value, just take the negative of what's less than and stick it on the other side.
Okay.
So the absolute value of x being less than 5 is the same thing as x being between negative 5 and 5.
Okay.
It can be anything between those.
Anything between those, which are the numbers we were testing. 0, negative 3, 3, etc. Pi, negative pi, right?
Yeah.
What about square root of 2? Is that between negative 5 and 5?
Yes.
Yes.
Is it?
Yes.
Yeah.
Square root of 2, is that one too tricky? What is the square root of 2?
It's something
One,
between
like a
one.
definitive one.
Something between 1 and 2, right? Because what's the square root of 1? Square root of 1 is 1. What's the square root of 4? 2. So the square root of 2 has to be somewhere in between those. All right. Better to know how to argue it than how to say it. All right. Let's do our next one. So now we have the absolute value of 2x minus 1 is less than 5. Now when is that true? This is true when 2x minus 1 is a number between negative 5 and 5. If 2x minus 1 is between negative 5 and 5, then its absolute value will definitely be less than 5. So this is true when we have negative 5 is less than 2x minus 1 is less than 5. Same thing. Or if you want some stupid formula, get rid of the absolute value, add the other one on the end with the negative version of that number. But you can just think about it. When is this true? When this is true. Alright, now what do we do? Because we want to know the x's that make this thing true.
Substitute? Just guess.
We can treat this as two separate inequalities if we want.
Okay.
So I can treat this as negative 5 is less than 2x minus 1, and 2x minus 1 is less than 5. That's essentially what this is saying, right?
Okay.
It's saying this is true and this is true. So now we treat this as though we have an and on two inequalities. Good? Now, what information can we get from this? What do we do?
Add 1.
Add 1 to both sides. So you get negative 4 is less than 2x. Now what?
You divide by 2.
Multiply both sides by 1/2. Yeah, perfect. So we get negative 2 is less than x. Or if you prefer to write it as x is greater than negative 2.
Oh wait, yeah. Either or.
Okay, now looking at this one, what do we do?
Add 1.
Add 1 to both sides, so we get 2x is less than 6. Then what?
Divide by 2.
Multiply by 1/2, and we get x is less than 3. Okay, so we know that x is greater than negative 2, and x is less than 3. So x is greater than negative 2. We come up here. Here's minus 2. So we'll put a circle there. X is going that way. And x is less than 3. 3 somewhere like right there. So it's all the values between negative 2 and 3. Not including 3. Thank you. Like that. So now if you pick any number in that range, if you pick any x between negative 2 and 3, it's going to satisfy this equation.
Yes.
So if we try something like 2, 2 is between those. What's 2 times 2?
4.
Minus 1?
3.
Absolute value?
3. What?
Is absolute value of 3 less than 5?
Yes.
There we go. Try a number that's not between that. What's a number that's not between negative 2 and 3?
6.
6. What's 2 times 6?
12.
Minus 1?
11.
Absolute value?
11.
Less than 5?
No.
False. Perfect.
No. Yeah. Oh yeah.
No worries. No false. Okay, let's do another one of these. I don't want to do all of them. Let's just look at one that looks more interesting. Which one of those looks the most interesting?
F. That's
F? All right, we'll do F. So we have the absolute value of 5x plus 10 is greater than 15. Right? When does that happen? That happens when 5x plus 10 is between negative 15 and 15. So this is the same thing as negative 15 is less than the absolute value, or is less than 5x plus 10 is less than 15. Right?
Yeah. And you can write it as two separate.
Did we do something stupid?
We did something very stupid.
Okay.
Let's see. Plug in 10 here. What's 5 times 10? Plus 10. Is the absolute, take its absolute value? 60. Is that greater than 15?
Yeah.
Yeah? Okay, let's plug in 10 here. 5 times 10
50.
plus 10. Is that less than 15? No. So we have to be smart and don't just blindly think you memorize some formula to solve these problems. Right? So let's go back and let's think about this. When is 5x plus 10 greater than 15? Or sorry, when is the absolute value of 5x plus 10 greater than 15? That happens when 5x plus 10 is greater than 15. Or that happens when 5x plus 10, 5x plus 10 is less than negative 15. If 5x plus 10 is less than negative 15, if it comes out to negative 16, what's its absolute value? 16, which is greater than 15. So if this number is less than negative 15, or is more than 15, then its absolute value will be more than 15. You with me?
Yeah.
So don't be tricked by those. So one of them, when it was like this, it gave us an and of two inequalities. This one's going to give us an or of two inequalities. Notice one of them was saying it was less than. This one said it was less than some number. This one said it was greater than some number. If it's greater than some number, it's going to give you an or of two inequalities. If it's less than some number, it's going to give you an and of two inequalities. Make sense?
Yeah.
Okay. So now we solve these exactly the way you know them up. So what are we going to do first?
Subtract 10.
Subtract 10, so we get 5x is greater than 5. So x is greater than 1, right?
Yeah.
Now over here, what do we do?
Subtract 10.
Subtract 10, so we get 5x.
X is less than negative 20.
Perfect. So we get x is less than negative 5, right?
Yeah.
So now when we plot it, x is less than negative 5, that starts right here, that's going this way. And x is greater than 1, this was our 0. So that's going to start somewhere like right there and go this way. So x has to be one of these numbers or one of these numbers.
Okay.
Make sense?
Yeah.
Perfect. And then last thing, they just gave you some word problem, wanted you to express it as an equation. They said the height of a race car must be within 1 inch of 52 inches. Okay? I tell you that the height of a race car must be within 1 inch of 52 inches. So what does that mean? That means the height of the race car minus 52 its absolute value must be less than or equal to 1.
Okay.
That's how you express that as an equation. Good?
Yeah.
It's the example they gave, so it's one I wrote. Okay, then I'm supposed to remind you that you guys have a Chapter 1 test online that is due by the end of Sunday night. That's the upcoming Sunday. And that is it for new material. So we'll go ahead, take a break, and then when you come back, those of you who want to, I will then give you a sense of the foundations of math. You don't have to pay attention to this if you don't want to. You can just start working on your homework. Very well. All right. So you don't have to pay attention to the second part of the lecture if you don't want. You're fine to just continue working on your homework. The point of the second part of this lecture is, unfortunately, you guys are taught how to do mathematics in a very terrible way. You're taught brute force. Here's a type of problem. Here's a formula for this type of problem. Here's how you use the formula. Next. Which is an absolutely terrible way to learn, study, and understand mathematics. And the downside of this is most of you most likely have a very bad concept of even what math is, let alone what algebra is, what it is that you've supposedly been studying for. This is now your third year of it. And so that's the point of the rest of this, is to give you a sense for what math is relative to other fields and what exactly algebra is, the field that we're studying. So that's what we're going to dive into with the second part. So the second part, I like to start with the question of, what do you know? I want to know one thing that you for sure know, you're positive of. Just one thing. Maybe go ask a little kid. What's something they know? You look out there, you see the sky, anything occur to you? The sky's blue. All right. How many people know that the sky's blue? Does anyone know that the sky's blue? Do I need to go get a first grader in here and ask that question in front of a first grader? Make you guys all feel embarrassed? Do you know that the sky's blue? You don't? Is there anything that you know? I just want one thing that you know. The sky's blue? Is that a good one? That's at least one thing that you know. One thing you're sure of?
Okay. To me, the sky is blue. That's.
There's no such thing as to me, this is true. No, there's just truth. Your opinion on it is completely irrelevant. To you, 2 plus 2 equals 5. No, 2 plus 2 doesn't equal 5. Period. So it's either true or it's not true. All right, the sky is blue. Let's focus on that. Some people think that they know that the sky is blue. What's blue?
Color.
So is red. I'm asking you what blue is. I want to know what blue is. What's blue? You stumped? You don't know what blue is?
It's color.
So is red. I want to know what blue is. Tell me what blue is. And so if you want to give a precise definition for what blue is, you're going to have to say, well, light can be modeled as a photon. A photon can be modeled as a mathematical wave. Waves have a frequency. So when you look at the frequency of the light, if it's in some range, then we call that light blue. And now we know precisely what it means for something to be blue. And you're going to notice that 100% of the time that you have a precise definition, it's going to come back to some mathematical model. Mathematics is what underlies this type of precision. The other question I could have asked you is, what's the sky? Tell me when my finger reaches the sky. Am I there yet? No. Am I there yet? When do I get there? When exactly do I get there? Exactly. So, you say you know the sky is blue, but you struggle telling me what blue is, and you struggle telling me what the sky is. But you're convinced that this thing you don't know anything, that you don't know what it is, has this property that you don't know what it is. Now, we're not allowed to think like that in mathematics. We have to be very precise. We have to know with a capital K what it is that we're talking about. So now I can give you something that you can know with capital K. And we'll give it to you through reasoning, this one being deductive reasoning. What?
Do we need to do like section 1 through 6 or just the test?
Oh, I assume you still have homework, however she assigned it. I don't know how she picks your homework problems. But yes, you do have homework problems on 4, 5, and 6. For sure. Okay, so now I can give you something that you can actually know with capital K. If I tell you that all men are mortal, and I tell you that Socrates is a man, what do you know? Socrates is mortal. Wonderful. Now here is what you know, to make sure you're not getting confused by the statement. You do not know that all men are mortal. You do not know that Socrates is a man. You do not know that Socrates is mortal. What you know with capital K is that if all men are mortal and if Socrates is a man, then Socrates is mortal. That's what you know is true. And you do not have to be able to tell me what men are, what mortal means, or what Socrates is, to still know that this is 100% true. And I'll prove that to you. If instead of all men, I say all foo, or instead of mortal, I say do, and instead of Socrates, I say blah, is foo, then let's see what you know. If I tell you all foo are do, and blah is a foo, then what do you know?
Blah is a do.
Then you know blah is a do. Perfect. And so you don't need to know the particulars of what you're talking about in order to know that this whole implication is true. Is it true that all foo are do? I don't know. Is it true that blah is a foo? I don't know. Is it true that blah is a do? I don't know. What I know with capital K is that if all foo are do, and if blah is a foo, then blah is a do. That I know for sure. And we know that through deductive reasoning. That's an example of deductive reasoning. It's one of the ways that we come to know things. It's one of the ways that we justify statements. We justify it deductively. We know that this implies this. That's what's true. You'll notice that in mathematics, all the things you prove, all the theorems are if-then statements. The Pythagorean Theorem is if you have a right triangle whose legs have length a and b, then the hypotenuse of that triangle is c squared, or a squared plus b squared, I mean. Right? I think I said that slightly wrong, but I think you know the Pythagorean Theorem. It's an if-then statement. All theorems in mathematics are if-then statements, just like this. And so you use deductive reasoning to prove that they're true. Now, reasoning deductively isn't the only way that we come to validate statements as true. We also have inductive reasoning. What's inductive reasoning? It's the reasoning of, it always happens that way, so that's how I think it's going to happen. If I let go of this marker, what's going to fall? Or what's going to happen?
It's going to fall.
It's going to fall, right? Are you positive of that? Do you know with capital K that this is going to fall?
Yes.
No, for all you know, I drilled this out, stuck a piece of metal up in there, rigged a magnet in the ceiling that pulls down on this with the exact amount of force that gravity's pulling down, and when I let go, it hovers. It's highly, 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 highly unlikely, but still possible. You see? In this example, it's impossible for it to be false. It is never the case that all faux are do, all foo are do, all blah is a foo, and it ends up not being the case that blah is a do. You know that this implies this with a capital K. Impossible for it to be false. It is possible for me to drop this marker and have it hover in the air. Right?
No.
We just barely went over one example. For all you know, I hollowed it out, I stuck a metal rod in there, I rigged the magnet in the ceiling. Highly improbable, but is it possible?
Yeah.
This is what magicians do. They take common phenomena and they rig up some way of making it act a little bit differently. And you're surprised every time. Because they're playing on this fact that you expect every time I let this go it falls to the floor. Of course, that's not a guarantee. It's just highly, highly probable. Right? So that's inductive reasoning. That's the reasoning of it. It always happens that way, basically every time I see it. So I think it will keep happening that way. Finally, there's abductive reasoning. Abductive reasoning is roughly the it makes the most sense type reasoning. Give you an example of using your abductive reasoning. You've got a younger sibling, a 2-year-old sibling, they're in a room, you go put a chocolate chip cookie on a stool right in front of them, you walk out of the room, shut the door, wait 5 minutes, come back in, the cookie's gone, and the child has chocolate smeared all over their face with some crumbs. What's the conclusion? The child ate the cookie. Now, for all you know, when you left the room, you had another sibling hiding in the closet. When you left, they came out of the closet, they ate the cookie, saved a little piece, smeared it on the little kid's face, went back in the closet, hid. When you come back in, you think the little kid ate the cookie. Poor little kid gets blamed. Right? So that's an example of abductive reasoning. Oftentimes when we conclude something abductively, we say we conclude it beyond a reasonable doubt. So this is the type of reasoning that you have to use in like a court of law. This is the type of reasoning that we use in science. This is the type of reasoning we use in math. This is infallible. This is pretty good. This is very suspect. And you have to be careful. Now, deductive reasoning, logic is pretty much developing the rules for deductive reasoning. So logic is as basic a field as there is. Mathematics uses logic to come to conclusions. So in mathematics, we're allowed to use logic to come to our conclusions. In logic, we're not allowed to use math. Then when you get to the fields of science, like physics, in physics, you're allowed to use math and you're allowed to use logic. But you cannot use physics in your math. You cannot use physics in your logic. So physics uses math, uses logic, not the other way around. And in chemistry, you can use physics. In physics, you're not allowed to use your chemistry. In biology, you can use chemistry. If you're proving something in chemistry, you're not allowed to use biology. So here's a basic pyramid for what you presuppose. Everything above presupposes everything below. What we're interested in is a field here in math. So what exactly is a field of mathematics? A field of mathematics, we need to use this type of reasoning. We need to say, if these are true, then this is true. That's the type of reasoning we need to use, but we need our first statements that we can say if about. So they're the basic statements that we start with in a field, that we just assume are true. We don't prove they're true, we just assume they're true. And you might have heard about these statements before. We call them axioms. You ever heard of an axiom? You've never heard of an axiom? Postulate? Same thing. Postulate, axiom, same thing. So in any field of mathematics, if we were talking about Euclidean geometry here, Euclid, in his elements, he starts out with 5 postulates and 5 combinations. So he basically has 10 axioms. We'll just pretend there's 5. So you say these 5 statements are true. And you say, okay, if these 2 statements are true, what can I conclude? Same way you were thinking about these. If these 2 are true, we were able to conclude that. You say, if these 2 are true, what do those imply? And those imply together some other statement. And you say, well, what does this and this imply? And those together might imply some other statement. And then this together with this might imply some other statement. And you develop this mass web of if-then statements that are all true depending on your axioms. If your axioms are true, everything else is true. And so you develop this massive web to work with. And so when you're doing Euclidean geometry, there's only 5 postulates that you assume are true. That's it. Everything derives from those 5 postulates. That make sense? So now we get to algebra. What about algebra, the field that you're studying? It's the same thing. It's a field of math, just like any other field, and it has its basic axioms. Now these aren't all the axioms. We're missing 3 here, but this will give you the gist of it and give you a sense for what these axioms are and how you use them in math. So if we were developing algebra, if you were developing algebra with me, we would have started with these statements. We want to start with talking about 2 plus 2 equals 4. No, you don't know that. We need to prove that. You can't just go around saying that. We need to start with just these statements and prove that means 2 plus 2 equals 4. Everything has to be provable from just these few statements. And so all of algebra derives from just this right here. Now let's make sense of it. What does it say? It says for any numbers, any real numbers, x, y, and z, there exist operations. We call that one plus, and we call that one times, such that all these things hold. Assumption number 1. X plus y, a number plus a number, and a number times a number are always numbers. I can't plus 2 numbers together and not get a number. I can't times 2 numbers together and not get a number. That's one assumption. You can't prove that a number plus a number is a number. It's one of your basic assumptions. You use that to prove other things. Our next axiom here says x plus y is equal to y plus x. Or in other words, it doesn't matter what order you add in. We call that the, you know the name of that property? The commutative property for addition. You've probably heard that before. Similarly, x times y is the same thing as y times x. Commutative property for multiplication. There are tons of operations out there that don't have this property. We're assuming that plus and times do have this property. What else are we assuming? Associativity. That x plus y plus z is equal to x plus y plus z. In other words, if I add those 2 terms together first, then that term, it's the same as adding these 2 terms together first, then that term. Similarly with multiplication, x times y times z is the same thing as x times y times z. Again, there are some operations that are not associative. We're assuming that plus and times are associative. You can't prove it. We assume it. Next assumption. There exists some number 0 and some other number 1 such that x plus 0 equals x and x times 1 equals x. We call 0 the additive identity. Because when you add 0, it gives you back identity. It gives you back what you started with. We call 1 the multiplicative identity, because when you multiply by 1, it gives you back what you started with. Make sense? Next one, we assume that for any number x, there exists some other number y, such that x plus y equals 0. For any number you choose, I can always find some other number, such that their sum comes out to 0, the additive identity. Similarly, for any number you choose that's not equal to 0, I can find some other number y such that their product comes out to 1, the multiplicative identity. Finally, we have distribution. If you have x times y plus z, that's the same thing as x times y plus x times z. And then our last assumption here is that 0 and 1 are different numbers. They're not the same number. And that's it. Those are our basic assumptions for algebra. And with that, we can start to define and prove things that you know and love and use all the time. For example, if I ask you, or for example, we can now define the number 2. How would we define the number 2? I would define the number 2 to be 1 plus 1. That's what I mean by 2. And now that symbol has meaning. Notice there was no 2 here before. There was only 0s and 1s. So 2 up to this point has been an undefined term. Now I just defined it to be 2 plus 1. Or sorry, to be 1 plus 1. Because we know what 1 is. That was a symbol given to us. We know what plus is. That was an operation given to us. And we know what 1 is. That was a symbol given to us. And so now we can define 2. Similarly, we can define 3. What would we define 3 to be?
2 plus 1.
2 plus 1. And now we can define 4. And it can be 3 plus 1. 2 plus 2 happens to work. And now we can prove something. Like, is it true that 4 is equal to 2 plus 2? And we can prove that. So we start out with 2 plus 2. What does that equal to? Well, I know that 2 plus, I know what 2 is. 2 is equal to 1 plus 1. By definition. Right? Now, I know that this is equal to 2 plus 1 using one of my axioms, associativity. Axiom 3 says I can go from here to here. It says rather than putting my parentheses there, I can put my parentheses there. Now, what is 2 plus 1 by definition?
3.
3. So this is equal to 3 plus 1. And now, what is 3 plus 1 by definition? 4. And that is how you would actually prove 2 plus 2 is equal to 4. Not quite as trivial as you might think some of these things are. And so now you can see how you can prove any sum is any number that it is. It would just be a lot of work to prove something like 10 plus 10 is 20. Right? So that gets us started out the door. We now have definitions for all our natural numbers. 0 and 1 were given to us by our axioms. Now we can define 2, define 3, define 4, define 5, define 6, etc. Question, what's the definition of 1?
Non-zero.
It doesn't have a definition. So this is another thing that you need to understand in mathematics. In mathematics, we talk about one of 4 things. You have what we call our undefined terms. Then we have our axioms. Then we have our definitions. And then we have our theorems. And all of math, everything you talk about math is one of those 4 things. Theorems, that's what you're proving all the time. Definitions, we create definitions all the time. You see it in your book. New definition, new definition. We define the absolute value function. So theorems and definitions are what you use the most. Axioms are your beginning assumptions. These are assumptions that you can't prove. You just have to assume they're true. What are your undefined terms? Those are the terms used in your axioms. You can't define everything. When you look up a definition of a word in a dictionary, what does it give you? A bunch of other words. It says this word is all these other words. Right? Then if you were to go look up all those other words, what would you get? A bunch of other words. And you go look up all those words, what do you get? And eventually, if you keep repeating the cycle, you're eventually going to get a circular definition. In trying to define the word, you're eventually going to have one of the definitions using the word you're trying to define. It's going to ultimately be a circular definition. So you can't sit here and look up forever and ever and say, what's the definition of this? Okay, well, what are the definitions of these things? Okay, well, what are the definitions of these things? You can't do that forever. You have to have a starting point. So our starting terms are the terms we use in our axioms. And they don't have a definition. Because you can't define everything. So plus does not have a definition, times does not have a definition, 0 does not have a definition, 1 does not have a definition. If someone asks you what's the definition of 1, it's a bad question. But every other number has a definition. And we define it in terms of the things in our axioms. Make sense? Alright, so that gives you a sense of the foundation. And now you know how we could start defining all the numbers like 2, 3, 4, 5, 6, etc. But if I ask you now, okay, what about the definition of a number like 1/2? What would we define 1/2 to be?
Half of 1. So.
But you're trying to use the concept now of the half. So we're in trouble, so we can't quite define everything yet. We know how to define all the positive whole numbers. But we'd have to start developing our field of mathematics to get to the point where we could start defining fractions. So I'll give you a sense for how some of these go. The first theorem we would prove is that there is only one zero. That is, there exists. When you see an exclamation point after there exists, that means one and only one. There exists one and only one zero in the real numbers. So if we were to do this proof, write it out in plain English. There exists one and only one zero in the real numbers. And so let's prove that. How do we prove that there's one and only one zero in the real numbers? We're going to prove this by contradiction. We're going to assume that there's 2 and show that's impossible. Therefore, there's only 1. That make sense? So we say assume by way of contradiction that there exists some other number. What should we call the number? We need to make up a symbol for it. We'll call it triangle. There exists some other number, we'll call it triangle, such that x plus triangle is always equal to x, and triangle is a number different from 0. We're going to show that's impossible, and triangle is actually the same thing as 0, only using our axioms. So 2. Then x plus triangle, what would be the best way to do this? We'll start with then 0. Then 0. Should have thought about these a little bit more before I tried to do this. Then 0 is equal to, oh, duh. Okay. Then triangle is equal to triangle plus 0. How do I know that? Triangle is equal to triangle plus 0. That is using this axiom right here. Axiom 4 says anything plus 0 is just that thing. So anything plus 0 is just that thing. So from here to here, we're using axiom 4. Then I'm going to write that's the same thing as 0 plus triangle. How do I know that I can change the order? That's using axiom 2. Right? And then that is equal to just 0 by assumption of triangle. What did I assume triangle was? Triangle is a special number such that anything plus triangle just gives you that thing. Anything plus triangle just gives you that thing. So I have triangle is equal to triangle plus circle, is equal to circle plus triangle, is equal to, or sorry, 0. That was 0, is equal to 0. What did I show? Triangle is equal to 0. But we assume that triangle is not equal to 0. Contradiction. That's our symbol for contradiction. Therefore, no such triangle exists. And we're done with our proof. So what did we just barely prove? We proved that 0 is the only number that has this special property. That if you add it to anything, it gives you back the same number. Only 0 has that special property. No other number has that special property. If any other number did have that special property, they would in fact be equal to 0. So 0 is the only one. That's what we just proved here. Alright, second proof. Let's prove that if x plus z is equal to y plus z, then x is equal to y. Piece of logic we use all the time, we call that subtract the same thing from both sides. How do you know that's a valid operation? So we're going to do the proof if x plus z is equal to y plus z, comma, then x is equal to y. That's what we're trying to prove. All right. How are we going to prove this one? When you're trying to prove an if-then statement, you assume this is true and show that implies this is true. So I say, let x, y, and z be real numbers in R, be real numbers, such that x plus z is equal to y plus z. And I need to show that that ultimately leads to y is equal to, or I need to show that leads to x is equal to y. Alright, so that's what we have so far. Now step 2, we're going to have to use some of our axioms. Now we're going to notice that there's this special axiom, Axiom 5. What does Axiom 5 say? It says for any number x, there exists some other number, call it y, such that their sum is equal to 0. For any number you choose, I can find some other number such that their sum is 0. That's what Axiom 5 guarantees. So I know, since z is a real number, comma, then there must exist some other number, I'll call it z prime, it's just a variable, doesn't matter what we call it, then there must exist some other number z prime in R, such that their sum is equal to 0. Z plus Z prime is equal to 0. That's using Axiom 5. Axiom 5 says that for any number you have, as long as it's a number, then there must exist some other number, we're just going to call Z prime, such that their sum is equal to 0. That's what Axiom 5 tells us. It tells us for any number, there exists some other number such that their sum is 0. So what is Z prime? It is a special number that when you add it to Z, you get 0. So 3. Then we know that x plus z prime is equal to y plus z prime. Right? If that is identical to that, then the z primes doesn't change anything. Now what is z plus z prime? How did we define z prime? We said z prime is a number such that when you add to z, you get 0. So z plus z prime is? 0. So this is going to be, we can rewrite this as x plus 0 is equal to y plus 0. Now what is x plus 0? It's just x. By definition, 0 is the additive identity. It is a number such that if you add it to a variable, you get just back that variable. So not by definition 0, but from Axiom 4, we know that x plus 0 is equal to x. And y plus 0 is equal to y. So we just really showed x is equal to y. And we're done. So we showed if x plus z is equal to y plus z, then x is equal to y. And we could continue on our merry way, proving all these theorems and creating definitions along the way. And that's how every field of math goes. So you start with just your axioms and your undefined terms. Here's our axioms. Our undefined terms over here are plus, times, 0, 1, and number. And then we just start proving a bunch of theorems and creating definitions along the way. And that's what every field of mathematics is. Doesn't matter if you talk about algebra, doesn't matter if you talk about geometry, doesn't matter if you talk about topology, doesn't matter if you talk about computation theory. Whatever the field, you do this exact process. You start with just your axioms and your undefined terms. You create useful definitions and start proving theorems. And that's it. So there you go. Gave you a little bit of foundations of math. We'll end the lecture there. I upload all the lectures to my YouTube page.